Hello and welcome to the 6th video of the FP3 chapter, Vectors. Starter question on the screen here to review something from P4 that we will use in this video. Find the point of intersection of the following two lines. I hope you note that we can just equate these two and find a lambda and a mu that makes the equation true. So here are the two lines made equal to one another, because if there's a position vector of a point where they are both at the same point at the same time, the intersection, then this must equal this. And the question is, can we find a lambda and a mu to make this true? To do that, we can peel off the different I, j, and k components and form three equations. For I, we get this. For j, this. And for k, this. Now to make this easy for myself, what I'm going to do is combine these two, because if I add these two together, lambda disappears, and I get 4 is equal to 3 minus mu, which gives me a nice easy solution that mu is equal to -1. And then if I put it back into one of these, I'm going to put it back into this one here, and that will give me 3 plus lambda must equal 5, so lambda equals 2. And then I must check that they both agree in the third equation as well. Even though I don't need to use that to find them, I must check it agrees. So 2 times lambda gives me a 4, and -2 plus mu, which is -1, I have -3 equals -3, so I have verified that this is correct. And don't stop there, because the question wants the point of intersection, not the values of mu and lambda. So we need to put this back in to one of our original equations and find the position vector. So I'm going to put in lambda is equal to 2. So 3 plus 2 gives me a 5. 1 minus 4 gives me -3. And 1 minus 2 gives me -1. So this is the position vector of the point. So the point itself has coordinates 5 minus 3, -1. Okay, in this video we're going to solve problems involving points, lines and planes using a lot of the work that we've done so far. Specifically in the first half we're going to look at intersections and angles, and in the second half we'll look at distances. There'll be a halfway point there if you want to pause the video or stop it and go back to it another time, because this is quite a long video. So the reason we did that starter is because to find the point of intersection between a point and a plane, we can use a similar method. It's not exactly the same, but it's very similar. We substitute the general point from the line equation into the plane equation like we did before, and then solve it. And what that will do is it will give you a single equation, and when you solve it, you'll get the answer for lambda, and that will tell you where the point is. Or if the line is parallel to the plane and there is no point of intersection, then you won't get an equation that you can solve. Probably it will just give you a statement that doesn't make sense like this. So let's give this a go. It's a very similar idea. Find the point of intersection of the line L with this equation and the plane pi with this equation. So if r must equal this on this line and r must satisfy this equation in this plane, I can put this general point into this equation and see if there's a lambda that will make that true. If there is, that's my point. If there isn't, they don't intersect. so I prefer mine in column format. So we've got this plus lambda times 1, 1, 2, and this whole thing dot with 1, 2, 3 from the plane equation must equal 4 if there is a point of intersection. So I've taken this from the line equation and put it in place of r here in the plane equation. In order to do this dot product, I'm going to combine these using lambda just as an unknown. So we've got minus 1 plus lambda, 1 plus lambda, minus 5 plus 2 lambda. Dot that with 1, 2, 3 and follow the usual dot product rules. So we do this times this and so on. So we get minus 1 plus lambda times 1 plus 1 plus lambda times 2, so that's 2 plus 2 lambda, plus minus 5 plus 2 lambda times 3, so we've got minus 15 plus 6 lambda, and all of that must equal 4. So here, if you get to this point, and this is not an equation that's possible to solve, then there's no intersection. However, we've got an equation that we can solve, so we go ahead and we solve it. We've got 6, 7, 8, 9 lambdas. If I take all of this onto the other side, that gives me 18, which gives a nice number of 2 for lambda. And as before, I want to find the point, not just the value of lambda, so I need to put this lambda back into the equation here and find out the position vector of the point where this happens. So if I put lambda equals 2 back in there, I get minus 1 plus 2 is 1, 1 plus 2 is 3, and minus 5 plus 2 times 2, so that's minus 1. So the point where this happens is this, so the point has coordinates 1, 3, minus 1. And that is my final answer. It's a little bit different with planes. Actually, it's quite a lot different with planes. And that's because of this simple fact that if you've got two planes that intersect, they don't intersect at a point, they intersect with a line of intersection. And there are two methods, one that's explained in the textbook and one that is not in the textbook, which I actually prefer. So I'm going to do both of them. I'll run completely through the same question twice using each of the two methods, and you can choose which one you prefer. So the first one here, using this question as an example to help explain it, is to use the Cartesian equation of the planes. So I'm going to change these into Cartesian form, eliminate one of the variables, and then basically rearrange things so that I can write three equations that I will equate at the end. Don't worry if that didn't make sense, it's difficult to understand without an example. So I'm going to go straight into it. So remember, R is our general point x, y, z, and I'm just going to do the dot product here. So we've got 2x minus 2y minus z equals 2, and that's the same information for that plane equation. Do the same thing over here. R is the same R if these intersect, so x, y, z is the same x, y, and z, so I've got x minus 3y plus z, and that has to equal 5. So I've got x minus 3y plus z must equal 5 from the second plane equation. And these two must be true at the same time along this line. So what I need to do is eliminate one of those variables. Well, here the easiest one to eliminate is z. If I just add these two equations together, I get 3x minus 5y is equal to 7. And the reason I do that is so that I can find an equation that connects x and y together without a z. And I can rearrange this as x equals 7 plus 5y divided by 3. And this is the first of my equations that I'm going to use as part of my answer. But I need to put that to one side now and find another equation that connects this same variable that I've chosen with the other variable z. So that's what I mean here. Rearrange your equations to find the same variable, the one that we're going to choose. In this case, I've chosen x, in terms of the other two separately. So I mean find two separate equations, one that connects x with y and one that connects x with z. So to do that, I'm going to do the exact opposite from here. I need to find y in terms of x. So that will be 3x minus 7 over 5. And the reason I need to do that is to put it into one of these equations. I'm going to put it in this one here to get rid of y and just have z's and x's in this equation. So that will give me 2x minus 2 times 3x minus 7 over 5 minus z is equal to 2. Make it a bit easier, I'll just multiply everything by 5. So we've got 10x, expand this out, minus 6x plus 14 minus 5z equals 10. So 4x is equal to, let's put the 5z on the other side, and then minus 4. So x is equal to 5z minus 4 over 4. And that is a lot of work, and it seems very strange, but the reason we can find use out of this is because we can now equate these equations, by which I mean this one and this one, because here we've got x is equal to something in terms of y, and here we've got x is equal to something in terms of z, and these two x's must be the same x's because it's all happening on the same line here. So we can say, put it in white, x equals 7 plus 5y over 3, which also must equal 5z minus 4 over 4. And if I tag on the end here that this can equal some constant, because of course x is just going to be a number once it's fixed on the point here, and whatever that point is on the line, you can fix it. And this you should recognize as the Cartesian form of the equation of a line. So we have our line, this is it. And if you want, if you don't like that, you can rearrange it into vector form again by, let's do that. So I would, if I was being really formal, I'd maybe write this, and then let's take the 5 out, y plus 7 over 5 divided by 3 over 5, and here take the 5 out as well. And then we can put that into vector form again by remembering that these numbers here, 0, 7 over 5, minus 4 over 5, are the values of the a vector, and the numbers underneath are the values of the b vector. So if you want this in vector form, I've almost run out of colours. Let's put it in blue. The final answer, the equation of that line in a plus lambda b form is 0, 7 over 5, minus 4 over 5, plus lambda times 1, 3 over 5, 4 over 5, like that. And that's a long process. There is an alternative method. The one I prefer uses the normals. So I'm going to do the whole question again using this different method, and you can see which one you prefer. So here we find the direction vector of this line by realizing that the normal to pi 1 is perpendicular to every vector in the plane, including this line of intersection. And the normal for pi 2 is perpendicular to every vector in that plane, including the line of intersection, because this, of course, to be a line of intersection, must be in both planes. So this direction vector is perpendicular to normal 1 and normal 2, and we can find that by doing the cross product n1 times n2. So the direction vector here is much easier to find. We can get it almost straight away because n1 is the normal of this plane, and then 2 is the normal here. So we can do 2 minus 1 cross with 1 minus 3, 1. And the top element, minus 2 minus 3 is minus 5. Middle element, minus 1 minus 2 is minus 3. And the bottom element, minus 6 minus minus 2 is minus 4. Now some of you might be thinking, wait a minute, that's different. If I go back for a second, you'll see, yes, it is. But don't forget, this is a direction vector. Any multiple of this is going to give me the same direction. And if you multiply this by minus 5, you get minus 5, minus 3, minus 4, which is what we've got here. So it is the same direction, even though the numbers are slightly different. And that, for me, and I hope you can see, that is much easier to get the direction vector in this method. However, the difficulty for this one is finding the position vector of a point on the line. And this takes a little bit of a sneaky trick. What we do here is we choose one of these x, y, or z to equal 0, and we substitute it into the plane equations. And this is a bit of a logical step. I've got x, y, z dot 2 minus 1 equals 2, and in the other one, x, y, z dot 1 minus 3, 1 is equal to 5, and the idea is this. If you've got planes, i.e. infinite planes, eventually the point on a plane will cross x equals 0 or y equals 0 or z equals 0. They will cross those axes at some point, somewhere on the plane. In fact, it will always be the case that two of these will be 0 at some point. Probably all three at some point will be 0. Not at the same time, but x will be 0 at some point, y will be 0 at some point, z will be 0 at some point, but it is possible that one of them won't be. But certainly two of them will be. So knowing that, we just say, okay, well, let's choose one of them to be 0 and make our equation easier to find a point, because all we need is one point that they share in common. So at some point, let's say z is going to be 0. And if this doesn't work, you just come back and you try x equals 0 or y equals 0 instead. One of them will work. So at some point, z will be 0. And at that point, let's hope we find the coordinates of x and y. And if we have found that, that's a point that is in both equations. So therefore, it's in both planes at the same time, which means it's on our line. And that will give us a in the line equation. So I get 2x minus 2y is equal to 2. And from this one, x minus 3y is equal to 5. And I combine these together. Let's double this up. 2x minus 6y is equal to 10. And subtract 1 from the other. So we get, let's have minus 4y is equal to 8. So y is equal to minus 2. And if y is equal to minus 2, let's just do this systematically so I don't make a mistake. We have x minus 3 times minus 2 plus 6 is equal to 5. So x is equal to minus 1. And this is both true when z is equal to 0. It's worked out, so we have a point that's on both planes and therefore must be on the line of intersection. And that point is minus 1, minus 2, 0. And we already knew the direction vector from the beginning with the cross product. And this is our line equation. And again, some of you might go, wait a minute, that's not the same either. And you're right, it isn't, but we don't need a specific point on the line. We just need any point that is on the line. So long as this is the correct direction vector and this is somewhere on the line, the equation itself, the numbers might look quite different. which is why we've got a different answer for the same line. Personally, I prefer that method. You, of course, can make your own choice. Here are the two summarized. Okay, moving on to angles. To find the angle between a line and a plane, or between two planes, I would say it's easier to use the normals. Find the angle made with the normal, or between the normals, and then use a good diagram and calculate the angle you need from there. So a quick idea here, finding the angle between this line and the plane here is difficult because there's an infinite number of vectors in this plane, and it's difficult to know exactly how to find that. If, however, you use the normal here, we have a way of finding this, because if we know this direction and we know this direction, then we can do the dot product. So finding, let me call it phi. Finding phi is not so bad because we use the direction vector of the line. And the normal vector of the plane. And we know that if we do b dot n, that equals the magnitude of b times the magnitude of n times the cosine of the angle between them, phi. And from there, given that the normal is always perpendicular to the plane, I can just do 90 minus phi to get theta. Whereas it's harder to do it here because I don't know this direction, whereas I do know the normal direction. So let's do that. 3, 4 minus 12 dot 2 minus 2 minus 1. And these numbers are quite easy because here we've got Pythagorean triples, so that's 13. And here we've got a 9, so that's 3. 6 minus 8 plus 12. So we've got a 10 and a 39. And then I have to grab my calculator. And it tells me that that is 75.1 to 3 decimal places. Sorry, 3 significant figures. So theta, coming back to my diagram, theta must be 90 minus phi. So 90 minus that is 14.9. And really, I should say 1 decimal place rather than 3 significant figures for an angle. And that is my final answer. Similar idea with planes, just be careful if you're being asked for the acute angle or the obtuse angle. So we want the acute angle here, but instead of doing this, because we don't know these directions within the plane, use the normals, which we do know, and that will give us the angle here. Well, technically it will give us, because of the directions, the angle here, but that's the same thing. If I call that alpha, and this is phi. And to get theta from that, 180 minus phi. So again, I just need to do the dot product. So we've got 4, 4 minus 7 dot 7 minus 4, 4 is equal to the magnitude 4 squared plus 4 squared plus 7 squared happens to be 81. So the square root of that is 9, and it's the same digits on the other one times the cosine of phi. And then we've got 28 minus 16 minus 28, so we get minus 16 is 81 cosine of phi. So the inverse cos minus 16 over 81 is our obtuse angle. And that is equal to 101.4. And therefore theta, which is 180 minus that, is 78.6. one decimal place. And if you think about the dot product and what it is that we're doing here and subtracting from 90 in the previous example and 180 here, then you could come up with these two fancy looking formulas, which is basically just the dot product and then taking the appropriate acute angle, and same here. But personally, I'd say instead of memorizing these, just use the dot product as you're familiar using it and make sure you have a good diagram. Okay, that is intersections and angles. The second half of the video is to look at problems involving distances. So to find the distance between a point and a plane, or between two planes, we start by looking at the distance between the origin and a plane. And that helps us find the other things. So to do this, I'm going to introduce something that is sometimes called resolving or sometimes called projection. But this idea here, that from the origin to the plane, the shortest distance will always follow the perpendicular distance, i.e. the perpendicular to the plane. So it will always be along the normal direction. And then any other vector on the plane r takes us to the general point on the plane, and that will always form a right-angled triangle because this will always be the normal. So this is your usual r minus a, and in this case a happens to be at the foot of the perpendicular. And of course we get the angle there, theta, which we probably don't know. Now the idea here is that if you take r, then we can find the magnitude of that in theory. And if we know theta, then the distance here, remember the normal is not usually anything to do with distance because it's just about the direction. It doesn't matter how big that arrow is. So let me call that d for a second. So the d there, between the origin and the plane, goes in the direction of n, but isn't necessarily the magnitude of n. In order to get that, we need a point on the plane, so this is r, times the cosine of theta. And you know that from basic trig. So here d is equal to magnitude of r cos theta. Now that's fine if you know what r is and if you know what theta is, but it's not very often you know the angle theta. So we're going to do a little sneaky trick here, and we're going to multiply this by 1. Now that doesn't do anything, you know that, but 1 also happens to be the magnitude of a unit vector. Any unit vector, all unit vectors. So what I'm going to do, I'm going up the screen because something else is going to appear at the bottom. What I'm going to do is call that 1 the magnitude of the unit vector n hat. So we've got the magnitude of r times cos theta times the magnitude of n hat. Because I know that will always be 1, and 1 times this doesn't change this. What that lets me do, though, is to do the magnitude of r times the magnitude of n hat times cosine theta, the angle between them, the directions. That's the dot product. And that is the dot product between r and n hat. Now that might not seem very useful either because we don't always know what n hat is, but we do know what n hat is if you remember how to find unit vectors. That is just r times, dot n divided by the magnitude of n. And if we know n, we know the magnitude of n. And this is a very useful thing. In fact, you'll hear me refer to this as projection. I think in the textbook it's resolving. But this idea here is that we have projected or resolved the vector r in the direction of the vector n. If you want to think about it as kind of like a light shining in this direction towards r, the light would make a shadow here. If this was a wall, shine a light this way, and the line here, the vector here, would make a shadow on the wall here. And if you stretched that out, the shadow wouldn't change, because as you stretch this out, r would get bigger, but so would the angle. and you wouldn't get any more of a shadow on the wall here. And if you brought it closer, 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 r would get smaller, so would theta, but the shadow would remain the same. Another way of thinking about it is kind of, this is the fixed direction, let's say x and y. It doesn't matter if you change y here, the x direction on the axis is still the same, because it's all on the same plane. It's not a very useful way of thinking about it though, because this is not usually the x direction. We're working in 3 dimensions, it's usually a random direction. So this idea of projection is more helpful. And this is an idea that we'll use in a few of these problems. So keep that in your mind. The resolved part of vector r in the direction of vector n is given by this. And I think this is given in the edXL formula booklet with an A, a B, and a B. Now, why is that particularly helpful? That is helpful because for a plane, we usually have this, or something like it, or something like this that we can find. And to change r.n into r.n hat, like I said, you just divide by the magnitude of n, and if you do that, that happens to equal the perpendicular distance from the origin, which was the thing we started off wanting to find. So if I just divide both sides by the magnitude of n, probably a vector that I'm going to know, p divided by the magnitude of n, that is the perpendicular distance, i.e. the shortest distance from the origin to that plane. And that is a very useful thing to be able to do. So r.n hat is equal to d, where d, or if you want to think of it like this, p over the magnitude of n, is the perpendicular distance of the plane from the origin. And in the example that follows, I'll explain how that helps us find any point to the plane or between two planes. This is the basic idea for all of these. So we have a plane pi, and that has equation this. The question is, find the perpendicular distance from the origin to the plane pi, from this point to plane pi, and from this point to the plane pi. It'll become clear why I've done all 3 of these by the end of the example. So from the origin to plane pi, we're using what we just talked about. r.n is equal to p, but if I divide this by magnitude of n, it is then equal to the very thing I want, the perpendicular distance from the origin to the plane. And we already have r.n. We have r.2, 1, minus 2 equals 6, that's the p. But if I divide that by the magnitude of n, which in this case is 2 squared plus 1 squared plus 2 squared, that's 9, the square root of 9, a nice easy 3. So if I divide that by 3 on both sides, then I get r.n hat equals 2, and that is the distance. That is the perpendicular distance from the origin to the plane. So my answer is perpendicular distance equals 2. And it's as easy as that. However, the point 2, 3, minus 3 to the plane pi is a little bit different. So what I'm going to do is clear this, keep this, and start drawing a little diagram over here. So we've got pi, and here's the origin, and from the origin to the plane is a distance of 2 units. For part B, what we're going to do is we're going to find a second plane parallel to the first plane that goes through this point, because it's easier to go from plane to plane, or more to the point, it's easier to go from the origin to a plane than to this specific point, because we're talking about perpendicular distances. So for part B, I'm going to have a second plane. I'm going to call that pi 2. So the original one was pi 1. In order to get that plane equation, it's very easy, because we know that the plane equation r dot n is equal to a dot n, and the key point here is if this plane is parallel to this plane, then two parallel planes must have the same normal direction. And this is where the fact that the magnitude of the normal doesn't make any difference is very useful, because it's the same direction for both, therefore it's the same vector for both, because we only are interested in the direction of the normal. So I can use that same normal. So r dot 2, 1, minus 2 is equal to a, this is where it's different. A dot n for pi 1 is 6. But this point is on a different plane, so I'm going to use this point for my a in pi 2. So 2, 3, minus 3 dot n, which is still 2, 1, minus 2. So that's 4 plus 3 plus 6 gives me a p of 13. And because I've used the same normal for both planes, the magnitude is still 3. So straight away from there I can write r dot n hat, dividing both sides by the magnitude, is 13 over 3. That now is d, the distance from the origin to plane 2. But that's not what we wanted. What we wanted was from this point to plane pi. But because we're talking about perpendicular distances, if that point is, say, over here, down to this plane here is the same distance as this point would be down to here, which is exactly 2 units closer than the origin, because we know the distance to pi 1 is 2. The distance all the way up to pi 2 is 13 over 3. So the distance between them, the distance that I actually want from the question, is 13 over 3 minus 2, which gives me 7 over 3. And that is the distance from this point, the perpendicular distance from this point to pi 1. Okay, the third one, same idea. Minus 5, minus 2, minus 4. Now there's a reason I'm doing this one as well. It's not exactly the same as part B. Same idea though. So we've got the same normal, same magnitude of the normal. The original distance was 2. Let's say the origin there. Pi 1 here. I'm going to call this one pi 3. So r dot the same normal, 2, 1, minus 2, is equal to, this case, a is minus 5, minus 2, minus 4, dot n, 2, 1, minus 2. So I'm doing the same thing. I'm creating a second, or in this case a third, plane parallel to the first. And I'm going to ask what is the distance from the origin to this plane, and then I'll use that to help me find the distance from this plane to this plane, which is the same as the distance from this point to this plane. So I've got minus 5, minus 2, and, sorry, minus 10, minus 2, and 8, which gives me minus 4. So r dot n is equal to minus 4 in this case. So again, we divide both sides by the magnitude of n to get n hat, and we get minus 4 over 3. But we can't have a negative distance. However, don't just ignore that, because it does mean something in this context. This is the difference between B and C here. This negative on the distance here tells you it's going in the opposite direction. So from here to this plane was 2 units, and this third plane is in the other direction. It's on the other side of the origin. And in this case, with my bad scale, that's 4/3. So the distance between these two planes is not the difference in terms of subtracting the values, but we're adding the magnitudes. So the total distance here is 2 plus 4/3, gives us 10/3. So be careful. I know it's easy to ignore a minus when you're talking about distances, because immediately you might think, oh, I can't have a negative distance, but there is an interpretation here for a negative distance. If it's the only one you're dealing with, that's not a problem. The distance is 4/3, but if you're dealing with two different planes, and one is positive and one is negative, it means they're on opposite sides of the origin. So be careful of that. Okay, for two lines in 3 dimensions, we need to be careful about what we're talking about. Parallel lines or skew lines. Now here, these do not intersect. This is not an intersection. I just can't draw this in 3 dimensions on a 2D screen. So here we've got the line, let's say this is going along the screen, and let's say this one is going into the screen and out of the screen. And in red, I've tried to show that as the shortest distance between these two. And of course, the shortest distance here is the same anywhere along these 2 lines. And the reason it's important to know which of these situations we're talking about is because the method is slightly different. The method is slightly different because here, your direction vector for both of your lines is the same. And here, it is not. Let me call it D. So that's why we've got different methods for these. So we're going to take these one at a time. First, we'll look at parallel lines. So I'll go through the general method and then go through an example, and then we'll move on to skew lines. So the general method here is to find a connecting vector between the 2 lines. And we can do that knowing that from the equation of the line, we have the position vector of a point on the line. So let me call that A on this one, and something different on this one, C. So we can connect these two to make a connecting vector C minus A between the 2 lines. And then we have to use this idea of projection or resolving. And we're going to apply it to this vector C minus A, and we're going to project as if shining a light down this way, projecting onto the direction vector here, which is B, from the equation of the line. Of course, it would be great if we could project that onto the red line. That would give us the distance that we need directly, but we don't know what that direction is. We do know B, however, because it's given in our line equation. So pretending the light comes down here would give a shadow along here about this long. And if I call that x, then I can write x is equal to C minus A projected on the direction B. So it looks a little bit different to this because this vector is C minus A, but it's the same idea. That you might see with magnitude signs around it, just in case it comes out as a negative, because obviously in the context that we're looking at here, this must be a positive value because it's going to be a distance. And if we can then also find the magnitude of C minus A, here we have a right angled triangle where the missing side here will be the side that I want, the perpendicular distance, therefore the shortest distance between these 2 lines. So this is the idea. This is the same idea that you can use for finding the distance between a point and a line, something that you've done in P4 with different methods, and the P4 method could be applied in this situation as well. I think it's about minimizing the vector by differentiating. Personally, I prefer this method. So this is the one I'm going to use in this example. Show that the shortest distance between the point this and the line with the equation this is this. And I've edited this question slightly to emphasize that it's the same method for a point and a line as it is between two parallel lines. So if this point is 2, 0, 1, and the line here has a position vector for point A given in the equation here, 1, 2, minus 1, then we know A straight away, and we know B from the equation as well, 5, 4, 3. And we can write, if this is capital C, position vector of that point is 2, 0, 1. And I hope that's enough to convince you that whether this line is here or not makes no difference, because that's going to be the same B. The important thing about the second line, if it's there, is the point on it. So now we apply our process. I want to find this distance here, the magnitude of C minus A. So we've got C minus A. Obviously, as a magnitude, you could do this the other way around. You could do A minus C as well. Minus A, 1, 2, minus 1, gives us 1, minus 2, and 2. And the magnitude of that is 3 units. Now I need to project that in this direction here, direction of the line, i.e. B, and to do that I apply my projection idea in the direction of B. Let me call this X again, and I'm going to put the magnitude around there just in case it comes out as a negative. So C minus A I've already got is 1 minus 2, 2, dot B, 5, 4, 3, and the magnitude of B, let me very quickly work that out over here, 5 squared plus 4 squared plus 3 squared. My calculator is 5 root 2. So this is 5 minus 8 plus 6 over 5 root 2, and that gives me minus 3, 3 over 5 root 2. Might be slightly easier if I rationalize the denominator. 3 root 2 over 10, and that is x down here. So all I have left to do is to apply Pythagoras. Oh, my lines aren't very good, are they? Apply Pythagoras to find the distance y. So y is 3 squared minus 3 root 2 over 10 squared, and all of that needs to be square rooted. And if you plug that on your calculator, you will get 21 root 2 over 10 as required by the question. For skew lines, we do a fairly similar idea. We connect the two lines with a vector using A and C again. So let's say over here A and over here C. So again, this is C minus A or A minus C. And we're going to project it again. So we're using this same idea, R dot n over the magnitude of n. But this time it is different because we're not trying to project it in this direction, and we're not trying to project it in this direction, we're trying to project it in this direction, the direction of the shortest distance. But we don't know that yet. What we know is it's perpendicular to this direction, which I'll call B, and it's also perpendicular to this direction, which I'll call D. And we do know how to find the direction of something that's perpendicular to two vectors. We can do the cross product. So the direction of the shortest distance is B cross D. Now that by itself doesn't tell us the distance, it just tells us this direction. To find the distance, we need to do the projection of C minus A in the direction of B cross D. So applying this formula here, we end up with C minus A projected in the direction of B cross D. And we have to divide by the magnitude of that thing that we're projecting in the direction of. And that will give us the shortest distance. Okay, maybe I should call that Y. And again, because it's a distance, if that does happen to come out negative, we should have the magnitude. So this is a formula that you might just want to remember. And you could, I think, in the book, make it a little bit more complex by saying the general point on this line and a general point on this line. But because C and A will be points on this line, I don't think you really need to go through that. But that's why it looks a little bit different in the textbook. It still gets down to this final answer though. So applying this in an example. Find the shortest distance between the two skew lines with equations this and this. So first of all, I'm going to make sure I know what is what. The position vector of a point on this line is 1, 2, 1, and the direction vector of this line is -2, -1, 1. Position vector of a point on this line is -1, 3, 2, and the direction vector of this line is 1, 1, -2. Now all I need to do is apply that formula. C minus A dot B cross D divided by the magnitude of B cross D, and ensure it's a positive value. So I do it step by step. C minus A down here gives me -1, 3, 2, -1, 2, 1 is -2, 1, 1, and B cross D -2, -1, 1 cross 1, 1, -2. The top element is 2 minus 1 is a 1, 1 minus 4 minus 3, and -2 minus -1 minus 1. Now I'll put this in my formula. So C minus A -2, 1, 1 dot 1 minus 3 minus 1 divided by the magnitude, oh I'm missing, magnitude of B cross D. So that's 9, 10 in the square root of 11. -2 minus 3 minus 1 over the square root of 11 gives me -6 over root 11, and of course the magnitude of this gives me 6 root 11 over 11 as my final answer. That's a lot of work going through all of these different sorts of problems, but hopefully that is enough for you to have a go at the questions from exercise 5F, and then to review the whole chapter on vectors, the chapter 5 review exercise in the textbook as well. And maybe I'll see you for matrices in chapter 6.